Dr. John McGregor, retired scientist from CSIRO, was kindly agreed to give this talk. And this is a IITM and CDAC combined talk. And it's good. John is the expert in computational fluid dynamics. So he developed the CCAM model, and CDAC is also actively involved in the computing. So so I'll briefly introduce this speaker. Dr. John McGregor obtained his PhD in computational fluid dynamics from Monash University. John has been conducting research into atmospheric model development and dynamical downscaling for over 40 years. He worked on several climate and weather models before developing the Darlan limited area atmospheric model, then the CCAM variable resolution global model, which is used at several institutions for climate downscaling. John's research include model development, model intercomparison, dynamical downscaling, numerical techniques, and physical parameterization. He is presently a retirement fellow at CSIRO Environment. With this, I would request our Honorable Secretary, Dr. Ravichandran, to kindly felicitate Dr. John. Yes. Oh. This is going to be the take a picture. Thank you. Thank you. Oh. But I give the talk there. So I'll put it on later. Thank you. So it's a great pleasure to be back here again. Is this turned on? Yeah. All right. So we have a very strong collaboration with South Africa. I've been visiting them each year for quite a long time, 10, 15 years. And on the way, I've stopped off in India, IITM, and other places several times. But it's good to resume after COVID this custom. So thank you for having me here. So today I'll talk about this model CCAM. And it's a variable resolution global model based upon the conformal cubic theory.
You can move your mobile phone.
Mobile?
Yes, yes, mobile.
Yeah, then you can use it.
That's interesting.
These modern technological problems. Okay. So I started this way back in 1997, this global model. But the important dynamical contribution through reversal redimension was about 2005. That's when the dynamics was pretty well completed. There's a lot of physics options, including convection spin low rate. We do have a couple of ocean that my colleague Marcus Thatcher developed on the same grid. We brought across the sea ice model from our other couple of models, and that's also on the same grid. So it's a very efficient model. It's highly vectorized. I think it's the fastest global model a long way anywhere around. That's due to the semi-Lagrangian dynamics that we use a large time step, but also the design. We've been very careful to make it very efficient. My colleague Marcus has also been doing some work on GPUs, but I won't go into that today. Mostly we use the model for climate downscaling, but we also do some specialized weather forecasting, and we do have a Windows version we developed some time ago. So today I'll talk about the model briefly, and then I'll show a couple of examples. I'll show a downscaled might run over in China, 5.4 kilometre resolution, that's pretty fine resolution. And then my colleagues in Vietnam are having trouble with this Harlem Bay flood event, so I've had an attempt at modelling that, so I'll show what we find there. My South African colleague, Francois, he's been interested in this Durban flood of last year, and he has conducted an interesting attribution study to see whether you can attribute specific events such as this flood to climate change. So he does doing an ensemble of 64 runs. And another one, the last one I'll show is some modelling to where my other colleague was having trouble with this hurricane Ian in Florida with the track. It's supposed to go north and then curve right and run into Florida. So he was having trouble doing it, and I said, I'll fix that for you. But I haven't quite succeeded. It also runs north. I have an interesting run where it does head the right way, but I don't understand that one. But I'll show that. Someone can tell me what's going on. So here's some pictures of the grid. So the original grid was thought of by Sidoni way back in the 70s, and he drew some grid lines on a cube and projected that onto the surface of the sphere. And it's much more uniform latitude longitude grid, but because the further edges of the cube, when you project to the sphere, they get a bit crowded. So along the edges, you can see the resolution is rather fine, and also at the vertices. Most people these days, well, the cube model has taken off quite a lot since I started in the 97 or so. But most of the other groups use the equiangular grid, and you take this grid, but you just project the angles. If you take a line around here, just project them so the angles going to the edge steps of the earth are equal, and that is much more uniform. That's called an equiangular grid. The one that I'll talk about today, CPM, is conformal cubic, and that was developed by Fedor Messinger and Jim Verser and Radchik in the late 90s. And that does a clever mapping where each of these grid lines on the sphere is orthogonal, which means the equations of motion are very simple. They're just like a Lambda conformal grid or polar stereographic with a map factor. You don't have to worry about contrarian covariant vectors and little complications like that. So that's what I'll describe today. But another variation of that is the equal area grid, and you can transform that one so each of the grid cells has an equal area. So I'll concentrate on the usual model here. Now, important for the work we do to be able to stretch the grid. So if you look back here, you see there are 6 panels. So you take one of your panels, say this one here, and this one here I've moved it over China. So that's one of the panels moved there, and then there's a zooming transformation. It's essentially sliding the latitude lines up and down this axis coming out of the page. That's called the slit transformation, and that's a very interesting transformation. It preserves the orthogonality and isotropy of the grid. So delta x equals delta y everywhere again, and the grid lines are orthogonal. So it's again exactly the same equations of motion, but the map factor, instead of being, well, map factor varies. It's to give this higher resolution over this panel, smaller resolution over here. Here is a summary of the properties. We use variable resolution through this transformation. Grid's orthogonal, delta x equals delta y. Semi-Lagrangian, which means you look where the parcels come from, and that removes the Coulomb number stability problem. In principle, you can have a parcel coming as far as you like, it will stay stable. In practice, you don't make it too big, you just want physics to have a certain reasonable time scale. And for the waves to be resolved properly. There's some other features, PVD vertical advection. Now, the unique feature is this unstaggered grid with reversible staggering. We'll say a bit more about that in a moment. No one else has scored 100 this year, which is surprising. But it has very good dispersion properties. Essentially as good as a spectral model for this sort of grid scales. There's minimal horizontal diffusion needed. We use Miller-like non-hydrostatic treatment, which is a very fast way of getting non-hydrostatic. There is some details. Semi-Lagrangian, that look where the parcels come from. With wind components, U and V, that can get a bit funny when you go over the edges of the boundaries. But if you use a Cartesian representation of those wind properties, then they go over the panel edges with no trouble at all. And we do have conservation of mass and moisture. It's a posteriori, which means the global integral is conserved, but there's some optimization method that tells you where you should change the mass and the moisture to get that conservation. So here is the picture of what the grid looks like. So here we have panel 0, 1, 2, for example. Every variable is saved where the dots are at the centre of this quadrilateral or a square little cell, and including the wind components, but during the semi-implicit gravity wave calculations, U and V are transformed to the edges of the cell. So U and V would have been at that dot here. For the gravity wave calculation, we'd like to have U at the edges in that X-type direction, V at the edges in that Y-type direction. And that's called the Arakawa C grid, if you believe that. And that is generally the best arrangement of your U and V components to give good dispersion properties for your gravity waves. And I won't show the analysis today, but the dispersion properties are essentially the same as highly regarded spectrum models. Two grid waves are actually preserved, and many people like to filter out two grid waves as fast as they can. You don't actually worry about that. Let them survive and look after themselves generally. But we do get a very good wind spectra, so I'll just show that. That again is the spectrum here. I won't say much about this. Is MPAS, Bill Scamarok did this. You should have these slopes, various wave numbers, and CCAM has a very similar behaviour to MPAS, which has a well-regulated negative energy spectrum. It's not the energy spectrum tells you what your real resolution of the model is. So you really want it to be close to those lines. The reversible staggering, I'll just mention how that's done. Here it's a simple enough method. If we have these whole numbers represent the centre of the cell, those dots I showed earlier, so U and V would be here, and we go around 4 panels of the on the sphere, so we go all the way around. It's a cyclic arrangement. But we've got U at these whole at the n minus 1 n and so forth. we would like to get U at the half values, minus half, plus half, plus 3 on 2. So the method that achieves that is to introduce a pivot point 3/4 of the way along, and we can say, well, the value at this 3/4 point is 3/4 of that plus a quarter of that one. Or you can also say it's 3/4 of that one plus a quarter of that one. So that gives you a simple tridiagonal equation. So if we know at the end and n plus 1 positions, that will let us solve the half values. And if we know these ones, that will let us solve the integer values. But that is actually a reversible process. You can go backwards and forwards without any loss, without any diffusion. It's not the same as interpolating the value itself. It's a little trick that keeps it exactly the same. This is just a higher order version, but even the simplest one gives you very good behaviour. I'll just briefly mention semi-Lagrangian. So here's the equation to notation. Semi-Lagrangian, you look upstream to see where the parcels come from, but you group the terms when you do that. So here's the new value of U. The U equation has pressure gradient terms and Coriolis terms, but you group it so that you have the new value of tau plus 1 actual group point. Is this plus the pressure gradient at that group point minus the Coriolis contribution, and then you relate it to the upwind value of that same combined quantity. Similar equation for the temperature, surface pressure, and if you introduce this height type variable big B, you get an equation where you can join them all together and you solve this capital value B. It's a Helmholtz equation with an eigenvalue decomposition. So don't worry about the details, but that's used in pretty well all the major weather services. They do a semi-Lagrangian solution, whether it's a spectral model or anything. And it's actually that's how it works. Now, mostly we've been doing downscaling for regional climate. That's what they were paying us to do, so that's what we did. And we do it a bit different way to a lot of others. Most groups, they take the host model, which may be the UK model, and then they set up a limited area grid inside it and force it to all the time. Lots of effort and data being passed around. But we do it a different way. Because here's an example of the SSTs from the CSIRO Mark III model. This shows the biases in January, and we see that the SSTs have biases of up to 3 or 4 degrees at various locations. You can try and correct your regional climate simulation later on for those biases, but it's a bit of a puzzle how you actually try and do that. So we do it right from the beginning. We correct those SSTs using present day monthly. We have a present day monthly correction for January. All the Januaries for 30 first 30 years, so, and that same correction is applied for the whole of that climate run. So we take those corrected SSTs, so driven by bias and variance corrected SSTs of the present day. So we take those by correcting by variance. We try to correct for biases in El Niños and La Niñas. We have a method where you can correct both bias and variance. So we run a uniform, quasi-uniform CCAM run, just driven by those SSTs and the CIs from the host run. So here's the grid. This is typically 100 kilometre route. And then we run the stretched version of the model, for example, over Northern India. And we force this run typically every 3 hours by the large scale features of this run. So we have a digital filter. On this scale, the digital filter is about the width of this panel here, the line panel. And these features coarser than that sort of length are inherited from the uniform resolution run, the 100 kilometre run. But any features at a smaller length scale do their own thing. So that's a very brief hint of what we do. But you can ask later if you want to know about that.
Can I ask a question?
Sure.
When you run this high resolution version, you can zoom and run the whole global model with the high resolution from India and then again through some separate.
I'm not sure if I understand, but the way we would run 1 month at a time. So we would run 1 month of this one, and while the data is still there, we use that to calculate the digital filter and apply it to this one at the same time. So it's a month of this one, a month of this one, keep on going like that.
So there's no two-way nesting, is it? Is there a two-way nesting or
No, it's not.
it's a one-way nesting?
Well, you've got almost 1.5 way nesting, I think. So, well, I guess really one way nesting, but it's not as restricted as normal one way nesting. Does that cover?
I think the LMDZ Shadows model, the French model, that's why I showed you over some area. The whole thing is all in one go. That's what I understand.
Okay. Well, the weather forecast I'll show later is like that in one go. And you can do the final one in one go also. But stretching it up to about three times stretching is there's much
That is there in the global model also. Presume lower area now. Outside the resolution is close. So this is also kind of, even the global model has like zooming in some areas.
Not really. It's higher resolution in those services, but that's not really relevant. But the stretching here, 100 kilometres to 14, it's about a ratio of 6 or 7. That's too strong stretching to stand alone. There have been studies done by Michel Becquet some years ago about the ideal stretching for standalone models. Just briefly mention physics. We have all the usual DCM type physics. 6-layer soil, I mentioned that molecules don't have so many layers of soil, 3 layers of snow. We've got a canopy spin, and those are fairly standard physics. The CSIRO cumulus convection scheme I wrote is a schematic of that. So it's a mass flux scheme, so you have the updraft from top of the boundary layer. We have entrainment, this goes up, entrainment as being subsidence in the environment. We do have a downdraft from usually about 3/4 of the way up, and then there's various moistening of the environment that goes on. So we're pretty happy with how that works. So now I'll just show example simulations. This was back in 2011. We ran over Lombok, east of Bali, and this was going from 200 kilometres, where are we? Was driven by a prior 200 kilometre run, down to 14, so it's a stretching of 14 times. So that's much more strongly stretched than other groups usually use. But because of the digital filter approach, we can do that. Not having some boundary where you must match radius going in and out. It's a much more tolerant approach. So that's probably still a world record for how strong we stretch these things. But that was quite a successful study. I think we used 6 simplified models in rate control, future climate at 2100, and we had a number of impacts we did all sorts of studies. So they had a long game. And Sulawesi as well. Here's the group here. There's Lombok in TV, Sulawesi out here, and a couple of papers, some papers written on both the Sulawesi and the Lombok NTV behaviour. So that was back in 2011. Computers were not quite as strong now, so we run higher resolution again, but that was not too good to do that. Another recent one I think that's done, we've been doing some bit comparisons with the Southeast Asia group. Most of the other members are running Red CM, but we have CPM and one or two other models, and that's a good excuse to visit Southeast Asia for their workshops. So don't mind doing that. So this is a very similar setup to Indonesian one, but now it's 100 kilometre the global run, uniform 100 kilometre run. And again, this was driven, I didn't do so many runs, but it's only the access GCM. The SSDCI drove this 100 kilometre run and then went straight down 5.5 kilometres, and the fraction now, the step factor is about 12. It's not quite as stretched as the one run, but very similar. The project proposal wanted people to run at 5 kilometres over various parts of Southeast Asia. Not many of the other groups actually managed to run at 5 kilometres. I found it a bit daunting, but Fredeline Tanggang of Malaysia, he ran over Malaysia, and I did over Indochina and Malaysia. So it doesn't take too long to run. It was about 4 years per day to run this one. Again, it's month by month, so you run 100 kilometres for a month, and then while you've got the data all available, then bounce down to this one, and at the same time I had this other grid over in Malaysia, a little bit smaller grid, but still 5 kilometre resolution. So they were both running month by month. This one was a little bit quicker, it's a smaller grid. It's about 65 days. So I'll do this and just results, what it looks like. This is showing DJF across here. Here's the 5 kilometre one over Indochina. This is showing rainfall. This is trim here, rainfall. So ideally that should look like that. So we're a bit wetter than trim along the east coast in that time, but being pretty regional agreement. We're a bit drier than trim over Malaysia, but our high resolution region is here. This is a little bit outside the high resolution region. This was the preliminary 100 kilometre run. So it ran 100 kilometres, drives 5 kilometre. So as you expect with the digital filter approach, there's similarities, quite strong similarities between those broadly. the rainfall from this one looks broadly like the rainfall from this one. And over here we have the Malaysian grid, and that was actually a bit dry this run. But again, that 100-kilometre run is driving this one, 100-kilometre driving that one. So ideally they all look like key to the but it's the monsoon season. We're pretty happy with those results as well. And climate change here is shown here. This is early. I won't go into details, but again, the 5-kilometre changes are broadly similar to 100-kilometre changes. But that's from the digital filter design with respect to that. It's helpful to have your host run somewhat similar to the fine scale run. Otherwise, it's a bit hard to explain what's going on. One heads up in a different direction. So this is a sensible arrangement to do things. Now I'll just show the three events. We have a quite good collaboration with them as well. And up to the Weather Service, we've been trying to model this flooding event at Ha Long Bay. So here is Vietnam down here. Ha Long Bay is very popular with tourists. That's China's up here. But they had this event that went on for 10 days and caused severe flooding near Ha Long Bay and over that region. There was a lot of damage. So you've seen most of it in the first 3 days of the simulation, and the moisture comes from the Bay of Bengal all the way across up here and drives into a low pressure system and causes all this trouble. So he was finding it difficult to model this off. Maybe it wasn't capturing the Bay of Bengal part of it, but I said I'll have a try. And, so that's the same grid I showed a moment ago for the 5-kilometre runs. But this time, referring to your question earlier, this is standalone. If you're running in a few days, there's no need to use a digital filter. It's the information is not coming from far enough away from Colorado. And so it's some runs both from GFS analysis and from ECWF. It turns out for this part of the ECWF, it includes a lot better analysis and captures some visual moisture rather better. So here was what I call the control simulation, the 4-day run. So here is Ha Long Bay area. So nice lot of rain here, the low pressure, developing about the right place, and this heavy rain, but quite reasonable. So, but I also was introduced sensitivity experiments to see if I had been set up in my convection scheme and radiation and so on. But there's a choice of outbased triggering, so this is one of the other options. This is not quite as good. It's not bad for the low. Here's the ECWF analysis. This one I showed a moment ago. It's similar, it's not looking like the same run. And this one is the corresponding, it's some small change, but the GFS analysis was not able to capture the high rainfall along the coast. It to put the rain somewhere else. And here's this control one again. It's worth mentioning when you get down to 5 kilometres, people argue about should you be doing parameterised convection or digital to resolve convection. In my experience, it's good to keep the parameterisation on as long as you can. This run here was reducing the parameterised and handing more of it over to the resolve. So it's not so good at capturing the event. So in the model, I have a formula
it's less parameterization.
This,
Less parameterization.
this one was less parameterization. Usually, this one here, parameterization, we've got done about 70 or 80% parameterized, and then the remainder is left to the results. And
We have partition it, and you're saying 70%.
I have a formula which depends on the grid length. And because it's variable resolution, it varies all over the globe. The actual local grid length, say it was low convective plant scale and so forth as well. But it means that as the grid length goes to zero, the convective spin goes off completely. As the grid length goes to 450 kilometres or more beyond 40, and then there's the calculation will come in.
Is it the scale aware in some sense? Parameterization. Scale aware parameter?
Yes, yes. So, okay, moving here. There's only a little bit more to go. So this, a little bit close in South Africa. So Francois, my colleague, was very interested in this. That was last year. So there was a lot of damage. A lot of people died actually, displaced, and a lot of rain. It's cut off low weather system. They often had these cut off lows, but this one was quite unusual, much stronger and more like a tropical cyclone in some of its characteristics. So this is the first one going to physics. Tomorrow. And the flooding was in Durban. But Francois, he wants to study this event, but he also would like to attribute whether it's due to climate change. So this is something quite new, I think, the event attribution. I hadn't heard of it until he told me about it, but there's other groups that are trying to do it as well. So the way he's attempting is a 64-member set of simulations he's carrying out, and with some plausible changes in the microphysics of convection. So I suggested a number of the convective ones still in for this. And so you have a simulation of the present world, which is the warm world, but using from your other climate change information, you know what a cold world would look like. You would have a cooler, colder SSDs, and then use this ensemble approach to evaluate it. So this is the grid we use. These are a lot more midpoints than I usually use. Down 3.8 kilometres. Durban's down here somewhere. So this is the control run. So there's a lot of rain. So he was pretty happy with the simulation. That's just using the normal model values. So luckily it behaved first time. And this is the cold world when you changes the SSTs to be what would have been a feasible cooler amount. So it's a lot less rain, and you looked at the structure of the storm. He hasn't done the ensemble one yet, but his conclusions were that deep surface flow was likely fueled by enhanced evaporation performance in SSTs, and so it's the first subtropical low to be ever identified south of 30 south, and the current load change from a cold core to a warm core system may be first, and he said there's a rainfall is probably 10 to 30% higher as a consequence of the climate change that's occurred up till now, and still has to do the large ensemble and proper evaluation. I'll just very briefly show my last event. My colleague Jack Cassidy, he was having trouble simulating the track of Hurricane Ian off Florida, which occurred last year. So I tried a few runs there. So I ran 25 kilometres. This is modest little stretch, then stretch a bit more. You can't quite see this, and then down to 6 kilometres. So the central pressure, as you expect, does get finer as you reduce the grid size. These were Jack's runs, all hands. The 3-day runs, it crosses over Cuba and goes pretty nice, more or less straight ahead. Whereas the observer track, after the second day, curves strongly to the right, actually without a Florida. So most operational models did not capture that curvature, or some of them, a couple of them did. I've been wondering what the problem, why we can't quite get it. So here's a 2-day. If you start a bit further on, it's still a bit to the west, that's Florida here. If you do a 1-day forecast after it's starting initial conditions after it's crossed through Cuba, then it's not too bad. It does head towards Cuba, towards Florida. It doesn't matter much whether I use a uniform grid or a stretch grid. It's the same resolution, 25 kilometres. The whole globe uniform, this is 25 kilometres stretched. They're pretty similar, that makes no difference. The European Centre Analysis, GFS, not much difference. This is showing the same one, uniform, showing the rainfall uniform grid versus the stretch grid, and GFS versus the European Centre on the bottom. And I've done extra runs more strongly stretched 6 kilometres, and still like to go north. I should mention these plots are on a 1 degree grid, so the resolution looks actually better if you plot it on a 0.2 degree grid. You do get a much lower central pressure. It's actually about 940, which is on the 1 degree grid, it's only about 950. I'll just go on to ran many sensitivity experiments, which not very much. Or didn't find the only thing that made a difference was cumulus mixing momentum that had some effect. That's instead that's the momentum one. Goes a little bit more to the east. However, the interesting one that I can't explain, I ran a 6 kilometre run, but I inadvertently used a large time step. Instead of running 90-second time step, I put 300 seconds. Being a 7-metre engine model, there's no problem using a large time step, or no real problem. That corresponds to a correct number of 1 for if the velocity is about 21 metres per second, but in the cyclone it will be rather larger than that. So ideally, I'd like to run with 90 seconds or 300. But here is the shrub here. It starts normal place, and it's towards Florida. And the last time it goes to Florida, but I can't work out why. The small times it's supposed to be more accurate normally. But I think one has a suggestion. Pleased to hear it. So that's most of what I'm saying. So we have a number of collaborations. The model is open source these days, so you can download it if you wish. My colleague Marcus actually he works away and give advice if needed. The strongest collaboration is with South Africa. It's actually not CSIRO now, it's Witwatersrand University, thanks to us, new establishments. But we've had large projects over Hanoi, the earlier one over Indonesia, and these various comparisons on them. So I'll stop there and take the question.
Thank you. Maybe we can take a couple of questions.
Schmidt filtering. Basically, isn't the Schmidt more of a spectral method which you are kind of putting together with your grid volume?
The Schmidt transformation.
Yeah.
That can be used in grid. It was originally, it's being used with the European Centre Model here for the arpège.
Okay, arpège, yeah.
But it can be used with any grid at all. I think originally it was
a spectral.
Yeah. I think it was conceived on a small video. But I think it was actually first really used in a spectral context.
Yeah, that's what I'm doing. Second question, I have a couple of them, sorry. Second is how do you suppress it to delta X?
We don't suppress them.
But then supposing it grows because of any kind of instability, what happens?
It doesn't grow because of a large way. There is legislative style definition, partial diffusion, which will control the growth of the small scale features. So there's no special filter or anything like that.
Is reversible staggering kind of playing a role of a smoothing filter for delta X oscillations?
Now preserves the difference. If they do delta X, it will stay there. But I think we have this good connectivity spectrum, and I think that is a result of preserving these small scale two delta X waves and these other features, not jumping on them and filtering everything up when you don't need to.
So the CTAN model was used in CMIP6. This was a coupled to the ocean model.
Not in CMIP6, no. We've been using it for them, it could be used, but the ocean model markers together probably not fully ready for CMIP6. But we have in Australia, we have the official CMIP model, which is Access, which is the UK atmospheric model and non-ocean model. This is an Australian model, not a foreign model.
You compare your CCAM high resolution downscaler with some of the other like CM or something. What computational cost wise which will be more efficient?
Oh, this is far more efficient. This runs very fast. Because it's similar ranking, one reason. Other regional models, I don't think of any that are similar ranking. Even Morph and Axiom has are not similar ranking. They've got the small timestamp, so they're quite expensive. The large weather centers, they come similar ranking. But also because of the cube structure, we think it's very high efficiency without message passing and parallelization. So we did have comparisons with the UK model, similar resolution. I think we're about 10 times faster, something like that.
I have a question about the reverse staggering. So the question is that what actually does that the model? Is this that the diagnostic what you do, or does that reverse staggering contribute to the prognostic evolution of the equation? So what does it actually has compared to the conventional staggering? So can you just enlighten me?
I missed the first part, sorry.
The reverse staggering.
Oh, reverse staggering.
Yeah. So what does it do with the prognostic evolution of the equation? So are they just a diagnostic, or are they contributing how the model itself evolves? So can you just enlighten with this sentence?
It's not diagnostic. It's part of calculating the gravity wave behavior. It's at the center of getting the gravity wave behavior. So, is that helpful?
Yeah. So is it conventionally used in numerical schemes?
Is it?
Conventionally used.
Oh, no, no one else is.
No, that's what I was curious to see how what does it does and what does it do to that finding some pivotal point and how does it balance its averaging and conservation principles in that point? What does that do to the numerical part?
I'll come to there are some groups who use non-stable grid and they will average it to the negative positions and do the WA calculation. There are one or two models do that. So it's in that family of models, but this is more accurate way to do it. There's been some interest from some of the other groups early on. John Thuber that's what the UK model management. He was wanting to see whether you could do it with the vertical behaviour, staggered and non-staggered vertical. So he was quite very interested there, but it's not so clear how you do that when you've got top and bottom boundary conditions. So here we have it's cycling, it's 4 panels all the way around. There's no boundaries. So it's especially suitable for a cube type model.
How good is your projection compared to the Q3 being adopted by EMSF recently? How good is the projection in P3? The answer people find the answer people that are adopting a final P3 of final permanent. Yeah. Is your technique almost the same?
I think that's a cube grid as well, isn't it? That's the first grid I showed. It's the grid itself is very similar, but I think they use a spectrum type method. They have a cell, and then they try to make it spectrally compatible with the adjacent cells, which is a complicated way to do it. There's a few groups do it that way. That's sort of the flavour of the month. But I haven't been tempted to go down that way myself. This reversible staggering has a lot of benefits that just automatically arise. There is, when I do the staggering, I showed that pivot point that can have a choice of 2 places. And so you could wonder whether it makes a difference whether you go to the left or to the right. So recently I've done a lot of extra runs and just to try and see if there's some ideal arrangement. But it doesn't make any difference at all, really. How do you do that?
So there's no more questions. There are no more questions. That is time, John, for a very nice talk. Everything has to leave. Thank you.
Hello. Please join party.